from this computer. Cool. So I sent the class an email yesterday afternoon. Not sure if you got it or not yet. If you haven't gotten it, you're going to want to check your email. It talks about whatever online homework is due, when, and also gives you the date of the test. So I want to actually look and make sure. Did I assign section 4.5 to you all last time? I think I might have. Let's see. 4.5. Oh, no, I didn't assign that yet. Okay. So the first thing that I'm going to do, oh, I know why I didn't. Okay, so check this out. We pretty much finished section 4.5 last time, but I usually like to be able to go through and, kind of guide you through the homework just to be sure you're all cool, knowing exactly what to do. So first thing I'm going to do is set the due date to be a week from today. And what I want to do is just say a couple things about the online homework section 4.5. There's not a ton of it. In fact, there's 3 questions. Wow, I didn't know there were so few questions. Isn't that kind of nice? Yeah. All right. So here they just want you to write what the vertical asymptote is. Okay, remember we had that at the end of class on Wednesday. We talked about the shifts and everything and what becomes our domain and our vertical asymptote. Here you're playing match. Match is fun, right? So you know that B and G are both what kind of functions? Exponential. They're exponential, and K and R are log functions. Okay, so here it's just a matter of playing match. And then right here, you're finding the domain. That's it. Don't forget to put your answer in interval notation. I really don't feel guilty assigning a section with 3 homework problems. Do you want me to add more? No. I'm kind of just joking, but okay. So that's going to be due a week from today. Cool. So the other announcement that I made in the email is your test on chapters 2 and 4 is going to be on Monday, November 14th in class. So not next week on Monday, it's a week from Monday. Okay. As with the other test, you can bring a sheet of paper with notes with whatever you want written on it. You need to bring a calculator. But yes, here's our test date. And this is actually the date that the syllabus listed. So we're pretty much right on, at least right now. Okay. But you need to be here to take the test. And I'm mostly saying this for the people who are listening to the recording of this. Of course, I'm saying it to everybody. Now, I will be making a test review. And that was one of the things that if the weather takes a nosedive this weekend, I certainly will have time to sit and do. So I will be making a test review on these 2 chapters. I'll be posting it on Moodle and it'll be around next week. Okay. Questions on any of this practical stuff? So what do we have? We have today, then there's next week, and then the week after. This is our test right there. Okay. What I want to say is I'll start 4.6 today. We've now gotten through the majority of this chapter. This is our one section left. And what we're going to be playing with are word problems. Like, okay, we've been talking about exponentials and logs. What are some real world applications to these things? On Monday, I'll continue my conversation on 4.6. If we need to talk about it next Wednesday, I certainly will. And I will also answer any questions you have. I don't know how hip you are on days off, upcoming days off, but next Tuesday, you have no classes, and next Friday, you have no classes. So we only have a 3-day work week next week, if we count school as our only work. Okay, so you only have classes Monday, Wednesday, Thursday next week, which means we have Friday off, which is also pretty sweet. Okay, but this is our plan of action. Any questions on that? All right, I just like to make it all really crystal clear. All right. So what we're going to be doing now is section 4.6. These are on exponential and log models. Word problems. Now, there's a few topics we're going to be talking about. Let me know if you have questions. Okay. All right. One of the things we're going to be talking about is radioactive decay. And I'm going to give you a definition here. Of course, you don't need to memorize any definitions. You just need to know what we're talking about and therefore how to apply it. Okay. And you might have heard of this term before. But one of the things we like to talk about of radioactive isotopes are their half-life. Okay. So the half-life of a radioactive isotope, and really anything, by definition, is the time. So when you talk about the half-life, you're talking about the time, and specifically the time it takes for half of the initial amount to decay. Have you heard that term before? Yeah, no. Well, now you have. Okay, that's actually how they do a lot of dating of from archaeological digs, right? They look at like how much carbon-14 is left in the substance, and they know that the half-life of carbon-14 is 5,730 years, and so that helps date how old that artifact is. Okay, so this is real life stuff. Yeah, cool. So for an exponential function, now, no, we have two ways of writing them. And we practice with the conversions back and forth, okay? What I want you to note is when it's in this form, you know it's decaying if B is between 0 and 1. And when it's in this form, you know it's decaying when K is negative. And specifically, what we're looking for when we talk about half-life is we want to find the value of T. Remember, the half-life is time. when the amount we have is 1/2 of the initial amount. Does that make sense how I wrote that out just now? Now we will take it a little bit further in a second. Right? Remember, the half-life is the time so that we have 1/2 of the initial amount. And our initial amount we've been representing with A. Questions here? Okay. Well, let's see what that looks like in each of these forms. In this form, we want to find the time, t. So for y equals a times b to the t, what we're looking for is the time t so that the amount of substance we have is 1/2 of the initial amount. Right? We want to find the time when we have 1/2 of our initial amount. You with me there? All right. Well, do you see how we have an A on both sides? We can divide both sides by A. So do you agree we're solving 1/2 is b to the t? How do you find your exponent, right? Again, we're looking for time. How would we get to this exponent? Take the log of both sides. Beautiful. Okay. If we have, if we have our exponential function written in this form, again, we want to find the time that we have 1/2 of our initial amount. Well, again, we have an A on both sides. We can divide both sides by it. So we have 1/2 is e to the kt. Notice in both of these situations, we want to get to our exponent. And Ross, right as you just said, the way we get to our exponent unknown is you take the log of both sides. So watch this. You get the log of 1/2 is the log of b to the t. What can I do with my exponent? Bring it down in front. So I have the natural log of 1/2 is t times the natural log of b. Can I solve for t? How do you get t alone? How do you get rid of what you're multiplying by? Divide both sides by the natural log of b. So we can say in general, if we have an exponential function in this form, the half-life is the natural log of 1/2 divided by the natural log of b. You cool there? Now we'll do specific examples. Over here, we can also solve for t. Now remember, k is some constant that's known. We know it's negative, okay? But you can take the natural log of both of those guys. And on the left, we get the natural log of 1/2. What's the natural log of e raised to a power? They cancel out. We're just left with kt. Right? These are inverses of each other. So if we wanted t alone over here, we would just divide both sides by k. So what we've done is we've now looked at this in general. You ready? Cool. Can I move this? Okay. So what if I tell you this? A scientist began with 250 milligrams of a radioactive substance. We're told that after 225 minutes, the sample decayed to 32 milligrams. And what we want to do is find the half-life of the substance. In some examples, you're going to be given your half-life and you're going to want to solve something. In other examples, you're going to be going the opposite way. All right, well, before we find the half-life, first thing we want to do is find the equation of the exponential function. That's like the unspoken direction. Now, in these situations, since we know how to convert back and forth, we can decide which version of the exponential function we want to play with. Do you have a preference which one we find the equation of? Okay, we can definitely find this on the right-hand side. Okay, what do we know right from the get-go? Don't we know A? What's our starting amount? 250. So thus far, do you agree we're here? I just plugged in my initial value. Okay, now we're given another piece of information. Notice when we want to find the equation of an exponential function, in this form, we need to find A and B. In this form, you're looking for your A and K. Okay, so we need to find our K. Well, what other piece of information are we given? Aren't we given that after 225 minutes, we have 32 milligrams? So I can say, so we're given that when T is 225, Y is equal to 32. So I can plug that in. 32 is 250 e to the 225K. You with me there? Do you see how I plug those values in? Okay, now we want to solve for K. Well, it's a good thing we learned how to solve exponential functions. Isn't our first step to isolate our exponential? In other words, we want to get rid of the number in front. How do we get rid of this 250? We divide both sides by 250. So I'm going to have 32 over 250, whatever the heck that is e to the 225K. God, I wish that was my balance in my bank account. Now, we want to get K. How do we get to our exponent? Take the log of both sides, and when you have the base of E, you totally want to natural log it. So if I take the natural log of both sides, I have the natural log of 32 over 250 is the natural log of E to the 225K. And the beautiful thing about what happens on my right-hand side is these are inverses of each other, so we're just left with 225K. If you have any questions, please, please, please ask. Now notice, we haven't even started to find the half-life. We're just trying to find the silly equation. Okay, well, how do we get K alone? Divide both sides by 225. So our decay constant is going to be whatever the natural log of 32 over 250 divided by 225 is. And this is when a calculator really comes in handy, as do my reading glasses. So we have the natural log of 32 divided by 250. And then I'll divide that whole thing by 225. So I get K to be negative 0.00. I'll just go 914. Doesn't it make sense that we got a negative value for K? Yep, because we're decaying. So I now have the equation of this exponential function. Wasn't that fun? Now, what was it we wanted to do here? Oh yeah, we wanted to find the half-life. Well, what does it mean to find the half-life? We want to find the time, t, when we have half of our initial amount. What is half of my initial amount? Well, what's 1/2 of 250? 125. Can I solve for t? What would be my first step? I would isolate my exponential. So I would first divide both sides by 250. And what's my next step from here? Take the natural log of both sides. And what am I left with on my right side since they're inverses? Isn't it negative 0.00914 t? Right? These guys are inverses of each other. So how do I get t alone? Divide both sides by negative 0.00914. So my half-life is going to be whatever the natural log of 1/2 divided by negative 0.00914 is. Now, something I want you to just notice, wasn't that consistent with what we saw in general? That my half-life is the natural log of 1/2 over k? Just saying. All right, so let's compute it. I have the natural log of 0.5 divided by negative 0.00914. And so I would say about 75.84 minutes. Or you could say about 76 minutes.
Question.
Yes.
What if, I'm just curious, I know we did it this way, would it be easier if you?
Let's do it the other way and you tell me which is better for you. Okay. So if we instead wanted to take this word problem and say, what if we wanted to get it in this form? I'll say, okay, first thing we know is that we're starting with 250. Now you don't have to do it both ways, but I want to show you that whichever way you do it, you're going to get to the same thing. So do you agree we can start out by saying that this is my function? Okay. Now, the other piece of information that we're given is that when t is 225, y is equal to 32. Right? Didn't we have that after 225 minutes? We were left with 32 milligrams. Hey, I want to solve for b. What's the first thing I would do to solve for b? Divide both sides by 250. So I'm going to have 32 over 250 is b to the 225th power. But I don't want b to the 225th power. I want b. How do you undo raising something to the 225th power? Nope, you only do log when your exponent's unknown. That's a great answer. No, oh, no, that's not messing up. You are so awesome. When your exponent is unknown, you do the logs. When your base is unknown, you raise both sides to the 1/225th power, or whatever exponent there is. So we would compute whatever 32/250 to the 1/225th power. Now, I'm sure that that's just intuitive to all of us, so we probably don't need our calculators to do that. I'm totally being sarcastic. But let's do it. We take 32 divided by 250. And I'm raising that to the 1 divided by 225th power. So I get B to be 0.9909. Now that I have this function, remember what we wanted to do is find the half-life, right? In other words, we want to find the time it takes for half of the initial amount. We've already gone through that. Half of 250 is 125. What would be my first step here for solving for t? Divide by 250. So we're going to get 1/2 is 0.9909 to the power of t. Notice I want my exponent. How do I get to my exponent? Log both sides. So we get the natural log of 1/2 is the natural log of 0.9909 to the power of t. The beautiful thing about taking the log of both sides is you can bring your exponent down in front. So in order to get t alone, we'll divide both sides by the natural log of 0.9909. And if you do that in your calculator, we'll take the natural log of 0.5 divided by the natural log of 0.9909. And notice we also get about the same answer. Isn't that cool? Questions there? So Ross, you asked which one's easier. I don't know that one's easier than the other. I guess it maybe depends upon which form you're more comfortable playing around with.
Probably the white is a AB.
Okay, and that's the one that we're most familiar with, right? I mean, that was our kind of our starting point. Okay. Now, what we just did is one half-life example where we started with a bunch of information and we wanted to find the half-life. Well, the other type of exercise you can be given that pertains to half-life is when you're given the half-life and you want to find something else. So do you want to do one of those examples? Great. So the half-life of carbon-14 is 5,730 years. And what we want to do is find the time it will take for 15% of the initial amount to remain or / be present. So as with most of our word problems, we should not even try to find the answer until we get the Silly equation. Okay? So while it's unstated, our first task is to find the equation. Okay? So I'll just use A times B to the T. Okay? Well, what information are we given for sure, for sure? What does my first sentence say? The half-life is 5,730 years. In other words, when T is 5,730, how much of our substance remains? By definition, isn't that 1/2 of the initial amount? Remember, of in math is multiply. Do you see how I got this? Cool. Well, we need to solve it. Do you see how we have an A on both sides? We can divide both sides by A. So aren't we solving 1/2 is B to the 5,730 power? Well, this is going to help us. How would we find B? Raise both sides to the 1/5,730 power. So what I'm going to put in is 0.5 to the 1 divided by 5730. And what we're going to get for B, I'm going to go many decimal places here because they're all really big to start with. 0.999879. So do you agree thus far our equation now is A times 0.999879 to the power of T? Yeah? What you would do is you would take 1/2. Can you see it? Yeah. Raised to the, now, I need to put my whole exponent in parentheses, so I do 1 divided by 5730. Yeah. All right. Now, something to note. Were we given our initial value? What's your off the cuff answer? Yeah, we weren't given our initial value. Okay, right. The only piece of information we had is what the half-life of carbon-14 is. Okay, but that helped us find B. But notice what our question is this. We want to find the time it'll take for what? For there to be 15% of the initial amount. So if A is my initial amount, what is 15% of A, at least mathematically? 0.15 A. Right? Of is times in math land. Do you see how I got this? Okay. Well, we want to find T. What do I do with this A first? We can divide both sides by it. So aren't we going to end up with 0.5 is 0.999879 to the power of T? I want my exponent. How do you get to your exponent? Take the log of both sides. So the natural log of 0.15 is the natural log of 0.999879 to the power of T. What's the awesome thing that happens on my right-hand side? I bring my T down in front. How do I get rid of this term here? Divide. Right, then I'm left with t on my right side, and on my left, I need to compute the natural log of 0.15 divided by the natural log of 0.999879. Oh my gosh, aren't you so curious? So natural log of 0.15 divided by the natural log of 0.999879. Kind of an easy number to remember once you say it like several times. Holy smokes! This thing is 15,678 years old. Whoa! You might as well feign interest or enthusiasm, right? Alex, we're making it up for you. Isn't that cool? All right, I want to do one more example today. And then we will break for the weekend and then jump back into this section next time. How does that sound? Cool. All right. New one. Oh, that's what it was. Oh, well. Let's just, oh, okay. Sorry, I'm just a mess over here. Okay.
Ask a question.
Oh, of course.
All right, so you assigned section 4.5, right?
Yeah.
For some reason, I don't have it showing up assigned on my end, and I don't know, maybe it's slow to read.
Oh, shoot. You know what? You're so awesome. I assigned it in my other Math 121 class. Hopefully yours is only 3 questions long as well. Let me assign it. Thank you. You're awesome. Boy, what would you have done all weekend? That's a great answer. Okay, now it's assigned. Thank you. All right, y'all ready? One more example for today. Thanks. Okay, so along the lines of half-life, there's also things called doubling time. And as you might intuit, the doubling time is the time it takes for the quantity to double. That's an intuitive definition anyhow, huh? Okay, so notice when we're talking about doubling time, it's obviously growing. Okay, now remember with the half-life, we were solving 1/2 is b to the t, or 1/2 is e to the kt. As you might guess, with doubling time, you're essentially solving 2 is equal to that. But you'll see that loud and clear in a second. Do you see how that makes sense? Okay, so suppose I tell you that a bacteria culture initially contains 1,500 bacteria, and it doubles in size every half hour. What we then want to do is find the size of the population after, how about 2 hours? And then do it for 100 minutes. Now, before we solve either one of those, don't we need the equation? Do you want me to find the equation in the form AB to the T or AE to the KT? Okay, I'm glad that we have a consensus. So we have Y is AB to the T. This time, are we given A? It initially contains 1500, so don't we have Y is 1500 B to the T? All right. Now, what piece of information are we given so that we can find our value of B? Well, we know that every half hour, it doubles. Okay, now I want you to note something. I'm looking ahead. Do you see how I want to solve this in this other part in minutes? You want to keep your units consistent. So what I'm going to do is have T be the time in minutes. Okay, you could have it be in hours, but then you're going to have to convert this 100 minutes to hours. You cool there? So in other words, when you have a couple different units, do the smaller units, it's easier. Okay, so what do we know? We know because the doubling time is a half hour, that when T is equal to 30, that's a half hour, we have double this population. Well, isn't that 3,000? All right, well, how do we solve for B? First thing we do is divide both sides by 1500. Oh, notice, we get 2 is B to the 30th. Check it out. Doesn't that jive with what we have right here? Oh boy. All right, how do we find B? Raise both sides to the 1/30 power. So if I compute 2 to the 1/30 power, I'm going to get B to be 1.0234. So now we have our equation. Well, for part A, what would we do? We want to find the population size after 2 hours. So what would we plug in? 2 hours is, wouldn't we plug in 120? And for part B, we would just plug in T equals 100. And I'm assuming you're okay doing the computation from here. I'm happy to do it, right? Like if we plug in 120, what do? We take 1.0234 raised to the 120th power, and then multiply that by 1500. So we're going to have 24,000. I'm just going to round to the nearest bacteria. 24,074 bacterias. Ew. Is that cool? Awesome. All right. That's it for today and the week. And I hope you have an awesome weekend. And I will see you Monday when we will be continuing this section. Cool. Thanks. I appreciate you.